Two-equation models are the most commonly used turbulence models in industry, so it's useful to understand how they work. Remember from an earlier slide that with eddy viscosity models, the system of equation is closed when the turbulent viscosity, mu t, has been determined. The way these models do this is purely through dimensional analysis. If you can define a length scale and a velocity scale that's associated with the turbulence, then you can formulate expressions for those scales that have the correct dimensions for the turbulent viscosity. The turbulent velocity scale is always the square root of the turbulent kinetic energy, and so virtually all of these models solve a transport equation for the turbulent kinetic energy, which we see here. The details of the individual terms in the equations are something that's discussed in the advanced turbulence training course. For the length scale, many different additional transport variables have been proposed, and again it's all based on dimensional arguments, and depending on what the variable is, then an expression for the eddy viscosity is determined by putting the two variables together in ways that give the right dimensions. So for the specific dissipation rate, omega, you can see that the expression for the turbulent viscosity is this should be proportional to the density times k divided by omega, and then this also gives expressions for the turbulent length scale and the turbulent kinetic energy in terms of the other variables. Other variables that have been proposed for use in two-equation models include the turbulent dissipation rate and the integral length scale of the turbulence. And you can see for either of these variables, you can see the expressions here on the slide that show how they're used to formulate the turbulent viscosity. The standard K-epsilon model was one of the first successful turbulence models that was proposed, and it still remains widely used, although it's possibly not the most accurate model in all cases. The model consists of transport equations for the turbulent kinetic energy, K, and the turbulent dissipation rate, epsilon. Each equation contains empirical constants that need to be determined from benchmark experiments of simple flows using air and water. The details of the equations are beyond the scope of this training. The important thing on the slide is to illustrate that the turbulence model consists of solving transport equations for K and epsilon, both of which contain some level of empiricism, and then using K and epsilon to determine the turbulent viscosity, which is what we need to close the RANS equations. In terms of RANS eddy viscosity models, and EVM stands for eddy viscosity model, the standard K-epsilon model is arguably the most widely used turbulence model for industrial applications. The model's parameters are calibrated using data from benchmark experiments like pipe flows and flat plate boundary layers. The model is robust and reasonably accurate for a wide range of applications, and it contains submodels that can be applied for flows that involve compressibility, buoyancy, combustion, and other phenomena. The model does have limitations. It performs poorly for flows with adverse pressure gradients, with strong separation, strong swirl, and large streamline curvature. It cannot accurately predict the spreading rate of round jets in an axisymmetric calculation, and in regions where you have large strain rate, like near a stagnation point, the model predicts excessive unphysical production of turbulent kinetic energy, which can result in inaccurate model predictions. The limitations of the standard K-epsilon model are well known, and as a result there have been many different variations of K-epsilon models that have been proposed to try to improve on its performance. One such model that's available in Fluent is called the realizable K-epsilon model. Its name comes from the fact that it enforces several realizability conditions for the Reynolds stresses. Its dissipation rate equation is derived in a slightly different way than the dissipation rate equation that's solved in the standard K-epsilon model. Compared to the standard model, the benefits of the realizable K-epsilon model are that it accurately predicts the spreading rate for both planar and round jets, and compared to the standard K-epsilon model, it's also likely to provide superior performance for flows where you have rotation, adverse pressure gradient, separation, and recirculation. So for these reasons, for general purpose flows, The realizable K-epsilon model is often preferred to the standard K-epsilon model. A one-equation model available in Fluent is a Spallart-Allmaras model. This model is a low-cost RANS model where a single transport equation is solved and the transport variable is the modified eddy viscosity. It was designed specifically for use in aerospace applications which involve wall-bounded flows, and is used mainly in aerospace and turbomachinery simulations. It's been shown to give good results for boundary layers that are subject to adverse pressure gradients. The model was intentionally designed to work well in a particular class of flows that are encountered in aerodynamics, namely wall-bounded flows and flows with mild separation and recirculation. It was never intended to be used for all possible complex engineering flows, and the model's authors do not claim it to be applicable for every possible situation, but it is popular for use in aerospace and turbomachinery applications. The two-equation eddy viscosity models in Fluent fall into one of two categories, K-epsilon-based models or K-omega-based models. With K-omega models, as the name indicates, the transport equation for the turbulent dissipation rate epsilon is replaced and an equation is solved for the specific dissipation rate, omega. We still solve the turbulent kinetic energy equation with the model, and the details of the omega equation can be found in the appendix if you're interested. K-omega models have become popular in recent years because they perform better than K-epsilon models in boundary layer flows, which means that for flows that involve separation, transition, low Reynolds number effects, and impingement, K-omega models are more accurate than K-epsilon models, and they're accurate and robust for a wide range of boundary layer flows with pressure gradient. In Fluent, two variations of the K-omega model are available. There's the standard K-omega model and the SST K-omega model.